So I hope it's being recorded now. Now we can start today's session. Okay. So like since I'm out of the chat room, can like anybody please confirm, like unmute and confirm whether the screen is visible to all of you? Like the PPT is visible? Hello? Okay. Yeah, like I can like if you send message over here, I can't see. So if like in between the class, if I ask you something, I want you to unmute and like answer. It's okay if you have issues with language or anything, doesn't matter. Like I'll try to comprehend what you want and then we can move accordingly. So it doesn't matter. So please unmute and answer if I'm asking anything. So we'll move on to today's session. So we'll start with the questions. So the first question is, with respect to the matrix of aluminum copper alloys, GP zones are, we have A, B, four options are there. So coherent, incoherent, semi-coherent and chemically indistinguishable. So if you look at these questions, we can say that it is from the precipitation hardening of aluminum copper alloys. So aluminum copper alloys will undergo a process known as precipitation hardening when they are quenched and then slowly heated. And they will have different types of AlCu2 precipitates that will be forming. And they're asking whether this particular type of precipitates are coherent, incoherent, semi-coherent, or chemically indistinguishable. So before we move on to the actual explanation, first we need to understand the difference between coherent and incoherent precipitates. So first is non-coherent precipitate or incoherent precipitate. The incoherent precipitate has no relationship with the crystal structure of the surrounding matrix. For example, if this is our actual matrix and this is the new precipitate that is being formed. So this is the aluminum single phase, and here the copper is like aluminum copper single phase is there, and a new precipitate is being formed, and it has an entirely different structure comparing to the surrounding, means that it is an incoherent precipitate. And suppose what happens, it is clearly related. Suppose this is a continuous boundary and there is a relationship between the phase over here and the phase that is formed as the precipitate, then we can say that it is a coherent precipitate. So this is the differentiation between non-coherent and coherent precipitate. So then we need to understand the precipitation hardening of aluminum copper alloys in order to answer this question. So what happens in case of aluminum copper alloys? This is the phase diagram of an aluminum copper alloy. So this is the weight percentage of copper that goes on increasing, and this is the 0% copper part. And this is the phase diagram. And what happens is that we will be first quenching the alloy to a point F. First it will be at a temperature M. And what happens? It will be a single phase alpha. And from that alpha phase, we'll quench it to a point F, and from F, this particular point will slowly start heating up to the point N. So this is the region where alpha plus Cual2 is the required precipitate. This is the region where alpha plus Cual2 is formed. So we can heat the material up to this to get the precipitate, because beyond this it will again become single phase alpha. So first we have our alloy at M, then we will quench it to F, and then we will slowly heat it to N. So while heating it to N, initially Cual2 precipitate doesn't form. It will move through a series of stages, and each of these stages will be having a particular type of precipitate, and that precipitate can either be coherent or incoherent with the lattice. So what is the first precipitate that is formed? So upon quenching from the solid solution alpha, copper atoms will start coming together and they will homogenate, and they will nucleate homogeneously, and initially GP zones or Guinear-Preston zones will be formed. These Guinea-Preston zones that are formed will be coherent with the lattice. So this is the first set of precipitates that are formed. They are not three-dimensional. So and these are coherent with the lattice. That precipitate will be continuous with the lattice. So then what happens? These GP sets will start growing and more three-dimensional precipitates will start forming. This more three-dimensional precipitate is known as theta double prime. What How does they become more three dimensional? These theta double prime precipitates can capture or incorporate the copper atoms more efficiently than the GP zones. These precipitates are also coherent. So GP zones are coherent, theta double prime is coherent. Then we have theta single prime. So what happens? So initially homogeneous nucleation was taking place, but then heterogeneous nucleation starts occurring at the defect. especially dislocations and stuff. And then what, theta single prime precipitates will be formed, and these precipitates are also coherent. So finally what happens, as time goes on, final COL2, that is the required precipitate, or the theta precipitate, will start nucleating at the grain boundaries and at the theta prime precipitate, and these precipitates are fully three dimensional, and at the same time they are incoherent. So these are our GP zones, and then they will form theta double prime, then theta single prime, and finally theta. So we have said that GP zones are coherent in nature, theta double prime is coherent in nature, theta single prime is also coherent in nature. Finally, theta precipitate will be incoherent in nature. So back to our question. With respect to the matrix of aluminum copper alloys, GP zones are. So I want any of you to now give me the answer. Like I had explained what type of precipitate GP zones are. So what will be the answer? Like somebody has unmuted, please answer. Hello? With respect to the matrix of aluminum copper alloys, GP zones are. It's okay if it is wrong or right. I can explain again. If you have any doubts, no issue. Please answer. Like only three of us are there. I don't think any new persons joined. So coherent. Yeah. Like Sai Prakash, if it would be better if you can unmute and speak, because otherwise every time I'll have to exit the window and come back and look. So it would be better if you can unmute and speak. So coherent. So I hope it's clear to all of you. Then we can move on to the next question. As compared to the engineering stress strain curve, so this is actually this engineering is extra. I'll remove that before submitting the PPT. As compared to the engineering stress strain curve, the true stress strain curve for a given material is, so lies above and to the left, below and to the right, crosses the engineering stress strain curve and is identical. So we all know about the normal stress strain curve, but normally we don't talk about the difference between the engineering stress strain curve and the true stress strain curve, but there is a difference, and we have to say which will be higher and which will be lesser, and that is this particular question. So first, what is a stress strain curve? A stress strain curve is obtained by elongating a sample, that is putting the sample under tension and then recording the stress strain variations until the specimen breaks. And what happens when we draw the engineering stress strain curve? What happens is that it is assumed that so when the material is being pulled, actually what happens, the material becomes thinner and thinner. But when we are drawing an engineering stress strain curve, we assume that the cross sectional area of the material does not change, but in reality it will decrease due to the elastic and plastic deformation that is happening. So the curve based on the original cross section is known as the engineering stress strain curve, and the curve based on the actual, the instantaneous. So if one particular moment we are measuring one value of stress and strain, and at that instant what is the area, so if a curve is drawn based on that, that is known as the true stress strain curve. So equations will be such that in case of engineering, stress is calculated by force by initial area, and true stress and true yeah and true stress will be calculated as sigma t is equal to force by instantaneous area. And at the same time, in case of strain, what is there, it is delta L by L0, that is the initial length, and true strain will be calculated as the integral delta L by L, that is the instantaneous length of the material. So what happens, as elongation happens, the L will be increasing, and here the area will be decreasing. So as we are pulling the specimen more and more, as the pull is being increased or the stress is being increased, what happens, the area will decrease and elongation will increase. Therefore what we can say, as area increases, the sigma t value will be greater than sigma for a given value of f, and at the same time strain, what will happen, this particular L value will be more compared to L0. Therefore strain will be lesser compared to the engineering strain. So when we have the stress strain curve, so this is the actual one, this is the engineering stress strain curve, and this is the true stress strain relationship. So therefore we can say that the what happens in a tensile stress, true stress is larger than the engineering stress, and true strain will be less than the engineering strain for a given point. And initially at lower values of stresses, they will be having an overlapping nature, but and as the plastic deformation goes on increasing, the difference between these two curves will go on increasing. So this is the difference between the two stress strain curve and the engineering stress strain curve. So from this particular figure now we can answer. So the true stress strain curve lies above and to the left of the engineering stress strain curve. So as compared to the engineering stress strain curve, true stress strain curve lies above and to the left. So then from this particular figure, we will be able to understand. So the explanation is that this instantaneous area will go on decreasing as we go pull and pull and pull and finally break the specimen. And in case of true strain, what will happen? The length will go on increasing. That is why true stress is more than engineering stress and true strain is less than engineering strain. So I hope it's clear. So the answer to this particular question will be option A, lies above and to the left. Is it clear to all of you? Okay. And what about Sai Prakash? Is it clear? Okay. So I hope first two questions are clear for you. And now we can move on to the next question. So atomic packing fraction of diamond cubic structure is dash. Usually we will be familiar with the atomic packing fraction of what BCC, FCC and things, but atomic packing fraction of diamond cubic structure. So in case of gate, it's not necessary that you understand. You can just by heart the values for BCC, FCC, diamond cubic and so on, and from that you might be already knowing the answer. But in case you're preparing for some kind of a descriptive examination, we might need to explain how we find this particular value, or there are several other questions that they can ask. So what is the total number of atoms in a diamond cubic structure, or the coordination number and those things. So in order to answer those type of questions also, we need to understand the explanation how we get that particular value. So actually, what is a diamond cubic crystal? A diamond cubic crystal is based on the face centered cubic lattice. So if you see here, if you can see carefully, we can see that this is basically a FCC lattice. Like this is one phase, we have center one atom is here. This is another phase, there is one central atom again, and the third phase, fourth phase, and all six phases, it will be having a central atom as well as corner atom. So this is basically an FCC lattice. And again, if you observe, we can say that at 1 by 4th distance from these corner atoms, there will be four other atoms that will be located. Therefore, we can say that it is a two atom basis at 0, 0, 0 and 1 by 4, 1 by 4, 1 by 4. So this is the case of a diamond cubic unit cell. So therefore, we can say that diamond cubic is based on the FCC Bravais lattice. Now we need to find out, usually when we are deriving the atomic packing fraction for BCC, FCC, etc., we will be having a relationship between R and the A value. So what are R and A values? R is the atomic radius of whatever atoms are present here, and A is the unit cell parameter. So we need to find a relationship between R and A. So how do we do that? First, the same cube, I'm just changing the orientation and I'm just keeping here. And we have corner atoms here, and at 1 by 4 distance there is one and another atom. So we know that XZ, this particular straight line, and in reality here, though we may be drawing like these atoms are at corners and they are not touching each other, in reality they will be touching each other. And therefore this is 2R and this is 2R, and from the center of this atom to the center of this atom, therefore the total distance will be 2R, because half R from here, half R from this atom. So XZ will be 2 times R. That is fixed. Now we need to find out the relationship between R and A, right? So first, what we will do in order to derive that, what we will be doing, first we will consider that this small distance, that is XW, is equal to A divided by 4. That is 1 by 4 distance, and it goes like XW. And from XW again at 1 by 4 distance, we will be having this vertical atom. So from Pythagoras theorem, then xy square will be equal to, this is like the overall condensed equation. The actual case is xy square will be equal to a by 4, xy square is equal to a by 4 the whole square plus a by 4 the whole square. Therefore, this 2 only. So what it will be? 2 a by 4, 2a square divided by 16. So we got xy. Now we need to find out from, again you can see the small triangle, that is x, z, y. Here again if we see it's a right angle triangle, and we can say that x z square in this case is equal to this distance plus this xy square. This distance again we know that it is a by 4. Therefore 2a square divided by 4, 2a, sorry, 2a square divided by 16 plus again a by 4 the whole square. Therefore in total it will become 3a square by 16. So this xz distance is equal to 3a square by 16, and this xz is also equal to 2 times r. Therefore, we can say that 2r square is equal to 3a square by 16. And on solving, we can say that atomic radius r is equal to root 3a divided by 8. So now we have the relationship between r and a, right? Now what will happen? So first, what is packing fraction? Packing fraction is having an equation, number of atoms into volume of one atom divided by the volume of the entire unit cell, where n is the number of atoms in the unit cell, V is the volume of the atom, and this is again a repetition. So, and volume of an atom divided by volume of unit cell. So that is this particular equation. And again, I'll go back to this figure. So we know that in an FCC lattice, there are 4 atoms per unit cell. So that calculation you might be knowing, like phase will be shared by 2, and therefore 6 phases, 6 into 1 by 2, that is 1 by 4. That will be in total 3 atoms. And again, corner atoms will be shared by 8, and therefore 1 by 8 into 8 corners, we will be having 1 atom. So FCC will be having total 4 atoms. In addition to those 4 atoms, we have at 1 by 4, again 4 atoms will be there. So what is the total number of atoms? 4 from FCC plus 4 that is present inside. So if you see this figure, we can say FCC lattice ones are the shaded balls, and the white ones are actually the atoms that are located at 1 by 4 distance. So total in this particular unit itself, we will be having 8 atoms. There are 8 atoms per unit cell, and each atom is tetrahedrally coordinated. So it has 4 nearest neighbors. So this is again a question that can be asked. What is the coordination number in a diamond cubic unit cell? Or they can ask how many atoms are there in a DC, etc. This is simple questions, and which can be directly answered, and you will get marks directly. So now we have all the required values. So atomic packing fraction is equal to total volume of atoms divided by total volume of unit cell. Total volume of atoms will be number of atoms into volume of one atom. And volume of unit cell will be the volume of this entire cube. Basically, it can be 8 into 4 by 3 pi r cube divided by a cube. And we know the relationship between r and a. We have derived that a is equal to 8 by root 3 r. So on solving this particular case, we will be getting root 3 pi by 16. And on solving, we will be getting 34 percentage. Like normally we might be knowing 34 percentage, but instead of by hearting, if possible, please go through the steps. Then you will be able to answer similar questions for all types of unit cells. So I hope this is clear, whatever we have been discussing with respect to the atomic packing fraction. Okay. And what about Sai Prakash? Okay. So that is clear. Okay. So this is the final question for today. So first is the yield strength of a polycrystalline material increases from 100 MPa to 145 MPa on decreasing the grain size from 64 microns to 25 microns. The yield strength of this metal in MPa having a grain size of 36 microns is, so that is how we will be doing. So if you can understand this question, it is based on the yield strength of a polycrystalline metal with respect to the grain size. And if you remember, this relation is given by what is known as the Hall-Petch equation. So sigma y is equal to sigma 0 plus k d raised to minus 1 by 2. So what is sigma y, sigma 0, k and d? Sigma y is the yield stress. Okay, and sigma 0 is a material constant for the starting stress of dislocation moment. So only if we provide a stress that is equivalent to sigma 0, it will start the dislocation moment. And k is a material specific strengthening coefficient, and d is the average grain diameter. So from this particular equation, if you see 100, a value 100 is given, a value 145 is given, and a value 64 is given, and 25 is given. So if you see, it can be put into the form of two equations which can be solved. So how we will be doing? It is given conditions that first is 100 MPa. 100 MPa is the strength for 64 grain size. 64 micrometers grain size. So 100 sigma y is equal to 100. Sigma 0 is a constant and k is also a constant, 64 power minus 1 by 2. So these are the two values. So yield strength is sigma y, that is given to us. Grain size, diameter of grain size is given, 64 is there. So if we substitute in this particular equation, we will be having 100 is equal to sigma 0 plus k, 64 power minus 1 by 2. That is the case. Then second equation, similarly we can write 145 is equal to sigma 0 plus k, 25 power minus 1 by 2. On solving these two equations, we will be getting the value of sigma 0 and k. So can you please solve this particular equation and tell me the values of k and sigma? So the case is 100 is equal to sigma 0. So if you want, you can note down 100 is equal to sigma 0 plus k, 64 power minus 1 by 2. 145 is equal to sigma 0 plus k, 25 power minus 1 by 2. So if you solve the values, you can get the values for k and sigma 0. So if you, it would be good if you can just solve and put in the chat box. What are the values? And I suggest that you start using the gate calculator, because it is not like it is similar to the normal scientific calculator, but it would be better that if you can on practice online how to very efficiently use the gate calculator. So have you started solving? K 600, okay. Then sigma 0, 125. Yeah, like is Sai Prakash also getting similar answers? Okay. Actually, you don't need to call me madam. It's fine if you can just call me Santra. I don't prefer the word madam actually. So this is the case. We have two equations. We will be using, we have found out the value of sigma 0. On solving, what we got, k is equal to 600 and sigma 0 is equal to 25. So that is the case. And now we have to find out the yield strength of this metal having a grain size of 36. Now the question is, they are asking us sigma y when D is given. We have solved and we have got the values of sigma 0. We have also got the value of K. And now we have to substitute this K sigma 0 and find out sigma y when D value is equal to 36 microns. So now we have sigma y is equal to sigma 0 plus k d power minus 1 by 2. Therefore, on substituting, what we will be getting, sigma y is equal to 25 plus 600, 36 power minus 1 by 2. Sigma y therefore will be equal to 125 megapascals. So the answer to this question is, the yield strength of polycrystalline material increases from 100 MPa to 145 MPa on decreasing the grain size from 64 to 25, and we have to find out the yield strength at 36, and we have got the answer as 125. So since we have like 30 minutes left, I'll discuss four more questions from the previous week so that you need not go through the recordings again. So next question is, so is this particular question clear for all of you that we have discussed now? Yeah. What about Sai Prakash? Okay. So now we'll discuss the next set. Okay. Match the following fracture surface features listed in group 1 with fracture mechanisms listed in group 2. So we know that whenever a material is being broken, it's said that fracture mechanisms are responsible, and there will be certain features present on the surface of these materials. So in group 1 we have different features like striations, dimples and microvoids, flat facets and river markings, dark surface with green safe, and so on. In group 2 we have different types of fracture that is given, and we are supposed to match these two sets. So first we will see how ductile fracture. Here there is an option for ductile fracture, right? So we will be seeing each of these fractures and how they will look under a microscope, and also to the naked eye how they will look. So first is ductile fracture in tension. So the specimen is ductile, something like steel or copper you can imagine, and the material is being pulled. And on pulling, what will happen? Eventually, it will break. And if you see a ductile specimen broken, we will be seeing that it will be having a cup and cone like pattern. So this is the lip part of the cup and cone. And when this particular region is seen under a microscope, what we can see? We can see what are known as dimples. These porous kind of an image, these porous things are known as dimples. And there are two possibility of failure in a particular material. There is a possibility that it can undergo fracture by transgranular ductile fracture or intergranular ductile fracture. Transgranular means if there are different grains, what will happen? Across the grains, through the middle of the grains, the specimen will start breaking. And for certain other specimens, what will happen? It will break across the grain boundary. So that is the two difference: transgranular ductile fracture and intergranular ductile fracture. And based on the type of ductile fracture, this is how transgranular ductile fracture will look under a microscope. And intergranular ductile fracture will be somewhat having a grainy appearance. So, and also what are actually these dimples? So actually inside the material there will be microvoids presence, and when the specimen is being pulled, there will be a particular crack will be initiated. It will start propagating, and due to that, eventually what happens? These microvoids will start coalescing or coming together with each other, and that is the reason why cup-like depressions are formed. And if a specimen is great, has greater ductility, for example comparing copper with steel, copper has more ductility. I think somebody joined now. Yeah. So actually we are 30 minutes into the session. So from next time, please try to join on time. So it's a like humble request from my side. Please try to join as early as possible. Okay? Yeah, yeah. Yeah, yeah. It's fine, it's fine, it's fine. It's fine. It's entirely fine. Actually, I want more students, that's all. So thank you for joining. Okay, we'll continue. So what happens is that suppose we are comparing copper with something like steel, it is more ductile, right? So because of the increased ductility, what will be happen? Yeah, yeah, I can hear you. Yeah. Okay, like you are like attending the session, right? You want to attend the session, right? Hello. Okay. Okay, fine, 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 fine. Oh, I thought you were joining late. That's why. Usually, many people join very late. Okay, 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 fine, fine, fine. Ah, it's fine, it's fine. Like I didn't know that. I thought you were a student. Yeah, sorry. Yeah. Okay. So what happens is that suppose we are comparing a material like copper with steel, what will be happening? It has a greater ductility, and because of this greater ductility, what we will be having? We will be having deeper dimples. In a similar manner, dimples can also be seen in torsion failure. So torsion failure, what happens? Instead of seeing these circular dimples, we will be some pattern kind of a skewed dimple can be formed. So that is the case of ductile fracture in tension. So now goes is brittle fracture in tension. So in case of brittle fracture, what we can see, the macroscopic surface, if you are seeing with the naked eye, instead of seeing a cup and cone like image, what we will be seeing, we will be seeing a very flat surface. And when we are observing this flat surface under the microscope, what we will be seeing, we will either be seeing something like this. This is known as the riverbed pattern, and this is known as the this is known as the decohesion of grain boundary. So what we can say, riverbed pattern is usually found in transgranular, that is across the grain, or a cleavage kind of brittle fracture. And in case of decohesion of grain boundaries is seen in intergranular brittle fracture. And similarly, if we see the surface, we can see something known as chevron marks. These V-shaped marks can be seen on the surface of brittle fracture. So chevron marks will be assessing the direction of crack propagation. So this particular can be used for assessing the direction of crack propagation. That is the case of brittle failure in tension. So our next option was fatigue failure. So fatigue failure, what happens? The material will be stressed continuously over longer periods of time, and eventually the material will fail. For example, roads, bridges, etc. They will be having some amount of constant load for a very prolonged period of time, and due to that they will fail. That is fatigue failure. And whenever we will be seeing a fatigue failure, on the macroscopic feature, we can see what are known as rashid marks. So this is what is known as rashid marks, and we can see on the macroscopic field. And when we are observing this under the microscope, we will be having this beach kind of pattern. These are known as beach marks. And similarly, we can also see striations. This is under the microscope. And if you see a steel specimen and so on, we can see the striations. These striations actually tell us the number of stress cycles that the material has experienced. So that is what we can see in case of fatigue fracture. So now we again come to our question. So we have to match striations with, immediately you can answer. We just discussed it is from fatigue fracture. Then dimples and microvoids we have, as we discussed initially, it is ductile fracture. So in case of answering match the following questions for competitive exam, it is a good idea that first, if we know two options, we can match them. So P is 4 and Q is 3. So P4, there is only one option here. So only by knowing one answer, we can get the correct answer. If you are completely sure about it. If you are not sure about it, you can match more options. But in our case, the answer is C. But nonetheless, flat facets and river markings are obtained in what kind of brittle fracture? Sorry, cleavage brittle fracture. And jagged surface with grain-like features are obtained in intergranular brittle fracture. So therefore, the answer to this particular question is option C. So I hope it's clear for all of you. Okay. And what about Kamesh? How to remember them? Like how these surfaces will be looking. Okay, so remembering, I would suggest that it's purely out of memory. There is no particular way in which we can predict. So whenever it's like whenever you say about ductile fracture, there are few words, key words that we need to keep in mind. Whenever you hear the word ductile fracture, first one is cup and cone. This is the cup, no, this is the cone, this is the cup. One is cup and cone fracture, then dimples. Dimples and cup and cone is the key word for ductile fracture. Now, when we are going for brittle fracture, there are two words. One is grainy appearance and then is riverbed pattern. At least if you forget grainy appearance, riverbed pattern is something you can give in mind. And just remember that riverbed pattern will occur when there is cleavage across the grains. And in case of fatigue, the thing is that beach marks or striations. So the striations you can keep in mind. See, there are multiple lines over here if you observe carefully, right? Like there are, like we can actually count the number of circular lines here. So these lines will be proportional to the number of cycles that repeatedly the material is undergoing stress, right? So that we can keep in mind, and beach marks. So and then, so I don't think there is a particular way in which we can logically remember. It's all based on memory. These kinds of questions or micrograph related questions are all based on memory somewhat. We cannot purely give a logical explanation where we can connect, except for things like the fatigue fracture where okay, there are number of striations, number of cycles, something like that. So is it clear? Yeah. Like based on my experience, I've seen only like some 2 3 questions from the fracture part. So but it's an easy scoring mark. Suppose you know just the basics, they, and every time they ask from fracture they usually ask only the basics. So and people usually skip this part because what happens, they find it difficult to remember. But remember that if you know just the basics, you can easily score 2 marks. So that is the thing with these kinds of questions. So next is determine the correctness or otherwise the following assertion and reasoning. So we have already discussed like precipitation hardening of aluminum copper alloy, right? So the peak aging time for aluminum weight percentage copper is indicated by maximum in hardness. Reason, maximum volume fraction of theta precipitate is formed at the peak aging time. So We had already discussed like what happens during the precipitation hardening in aluminum copper alloys. Initially it will be quenched, it will be slowly heated. Initially GP zones will be formed, then theta double prime, theta single prime, and theta will be formed. The first question that we have discussed was whether these precipitates are coherent or incoherent. But now the question is, we have one assertion, one reasoning. We have to find which of them is true and which of them is false. First is peak aging time for an aluminum copper alloy is indicated by a maximum in hardness. So whenever we are studying these kinds of materials, we will assess this aging by measuring their yield strength or hardness. Therefore, we can say that the assertion is true. So suppose you have a material, you have the alloy, and you are slowly heating it, and we need to find out whether the material has properly aged. Material has properly aged means it has been kept for the sufficient amount of time at sufficient temperature. So that is assessed by measuring its yield strength or hardness. Therefore the assertion is correct. Now next is the reason why they are like measured with yield strength, or why its maximum hardness at maximum aging. So if you see here, the maximum yield strength or maximum hardness occurs somewhere between theta double prime and theta single prime. Usually we will be saying it is about theta single prime, but actually it lies between theta double prime and theta single prime. But in our case, they are telling that maximum volume fraction of theta precipitates is formed at the peak aging time. But if you see here at theta, its material has actually overaged. Like after reaching maximum hardness, it is losing its required property. So in this particular case, assertion is true. Like the material is indicated by hardness or yield strength, that is true. But the reason maximum volume fraction of theta precipitates is formed at peak aging is false. If this theta was given as theta single prime, we can say that both A and R are true. But in our question, this is true and this is false. So is this clear? Okay. And what about Kamish? Okay. So, like multiple questions have been asked from this aluminum copper age hardening precipitate. So, it would be like if you are familiar with the concept and if you're lucky enough, I think you might get questions again. So, next is a very direct question from phase diagrams. Identify the type of following invariant reactions. Liquid 1 plus solid 1 gives solid 2. So options are eutectic, eutectoid, peritectic, peritectoid. So what are in? So first we will start as what are invariant reactions. So we all know the Gibbs phrase rule, that is F plus P is equal to C plus N. There are four terms. Now we need to answer what is meant by P. P is the number of phases that is present. F is the number of degrees of freedom or the number of independent variables that can be varied without changing the stability of the system. And then we have C, which gives us the number of components in system. And finally, N, we have the non-compositional variables like pressure and temperature. So that is the Gibbs phase rule. And in the Gibbs phase rule, this particular F becomes equal to 0. Those are known as invariant reaction. So what does it mean? It means that we cannot change either composition or temperature, because if we change the temperature or composition, it will go into a new region. So how do we explain that? So for example, this particular red point, this is the invariant reaction point. So if you remember, this will be the temperature axis in a phase diagram, this will be the composition axis. And at this point, if we temperature, it goes to a new phase. And if we change composition also, it goes into a new phase. Those are known as invariant reaction, and at this particular point, number of degrees of freedom will be equal to 0. And there are different types of invariant reactions. So if you know the iron carbon phase diagram, there are actually three invariant reactions. So it would be better, like if you can find out for the next class what is the three invariant reactions in an iron carbon phase diagram. So here we have multiple options. So metatectic and monotectic, it is not required that you try to memorize, but at least these four, it would be very good that if you familiarize. So eutectic means that a liquid will reversibly change into two solid phases. That is, at this particular point, L, if you decrease the temperature, L can directly become alpha plus beta, or alpha plus beta can go into the liquid phase. In case of eutectoid, what happens? Instead of liquid, a solid phase gamma will be there, and it will reversibly change into alpha plus beta. Peritectic means that liquid plus alpha will change to a solid phase beta. And peritectoid means that alpha plus beta will reversibly change into gamma. And here we can, if you notice, you can say that whenever there is a letter oid present, all three phases will be solids. That is the case. And instead of giving alpha, beta, gamma, they can also give solid 1, solid 2, and so on. So, what was our question? Liquid plus solid 1 gives solid 2, right? So, liquid plus solid 1 gives solid 2, and the answer will be peritectic invariant reaction. So, is this question clear? A new person has joined. Like, okay, he left. Wow, that was nice. Okay. So now we'll go to the last question from this session. So next is in an X-ray powder pattern of a simple cubic crystal, the second peak corresponds to dash. So many questions are asked from this particular region, X-ray diffraction. There are some 2 to 3 equations that you need to remember, and one particular important table is there. So what is the case? We know about extinction rules. If you've gone through the theory of X study, we know what are extinction rules, right? Extinction rules mean primitive or simple cubic unit cell. If we see the XRD pattern, any combination of Miller indices HKL values are possible. When we are seeing BCC, there is one condition that peaks will appear only at those points where HKL values are even. And in FCC, HKL will be either all odd or all even, but they cannot give mixed values. For FCC diamond, HKL should be all odd or even with the condition that their sum should be equal to 4 times N. HCP means that L should be even and H plus 2K should not be equal to 3N. So these are the allowed reflections. So at least primitive BCC and FCC you should keep in mind. So simple cubic means any HKL is possible. BCC means it can only be 2, 4, 6, 8 and those combinations. And in case of Miller indices, 0 is also considered as even. Then face centered means that it either can be combinations of odd numbers or even numbers, but they cannot be mixed. So second peak they are asking in simple cubic. We know that first peak what it will be. It cannot be 0, 0, 0. There's no plane, right? So first peak should be 1, 0, 0. Okay. So then second peak what it will be? It can be 110. So that is a very simple and direct question. For simple cubic, it occurs at first peak occurs at 100, second peak occurs at 110. And in XRD, there are two equations that you need to be very familiar with. One is the Bragg's law, 2d sine theta is equal to n lambda. Another one is the interplanar spacing equation. D is equal to a by root of h square plus k square plus l square. And at least for simple cubic systems, if you remember the values of D, it will be very good. So I hope all the questions that we discussed today are clear for all of you. In case you have any additional queries and feedback, email me at this particular email ID. Like any of these questions, you have any doubt or any concept you didn't find very clear, please note down this email ID and you can mail me as and when you feel free. So, is it clear to all of you? Like whatever we have discussed today? Okay, so if you have any suggestions or anything, please do email me. And now I'll give you the YouTube channel's ID, like whatever I've uploaded so far. Okay, so you can see the channel NPTL Interactive Sessions with Sandra. That is the channel's name. If you search, you can see there I have uploaded seven, maybe I think say yeah, 7 videos so far, and each video has 4 questions. These are very short videos, they're not very time consuming. You can just watch them in like 20 minutes or 25 minutes and so on, and you can familiarize with these concepts. And in even those set of questions, if you find any doubts, please do email me. So NPTL Interactive Sessions with Sandra. That is the channel. Like I will post it here. But okay. No, I'm not getting because I have an option for recording. So, like, are you have you like understood the name of the channel that you want to search in case you want to continue seeing those videos? NPTL Interactive Sessions with Sandra. Okay. So please feel free to ask any questions. Familiarize yourself with gate calculators. And in case you have any doubts and queries, please do approach me. like I'll be happy to solve your questions. So past weeks I have not been having any students. So in case anybody's like along with you, anybody's preparing for gate metallurgical engineering, ask them to join the sessions also. Just one a matter of 1 hour. So thank you for both for joining, and see you next week. Thank you so much. You may leave now. NPTEL interactive. Yeah. SANTHRA. The spelling is actually SANTHRA. NPTEL interactive sessions with Sandra. So that is the channel's name. So thank you, Sai. See you next week.